All right. Hello, everybody. Hello, hello. There we go. Good. Okay. Let's see. All right. Welcome. So today we're going to be talking about software engineering, but first, a quick word on exam. Okay. So let's see. One more thing. Turn off that noise that you can't hear earlier. All right. We all good? All right, good. Okay, so quick note on exam. So yeah, the last like couple, I don't know, month and a half have just been like crazy busy, and the exam was a little undercalibrated. So I will say when I write an exam, it is always one, way too long, and two, just vastly way too hard. And then using TA feedback, I pare it back to a sensible level. Got pretty close this time, but not close enough. So I've never done this before in 10 semesters teaching the class, but did like a mid-semester, pretty significant bin adjustment. Spent a lot of time. I was up till midnight or so because I didn't want the grades to come out and then you to, especially those of you who are LNS CS hopefuls, like have this like punch in the gut that's like, well, can't do CS now. So I hope that the bin shift gave you a sense of warmth, even if the exam scores were lower than you might have liked. But I think, it's not a bad exam. It's just that it wasn't calibrated against the bins that were created at the beginning of the class. I'll get it right on the final. So anyway, sorry about that. I know that it feels bad, but it's always good to know what you don't know. And hey, you can always pat yourself on the back that I think it was the hardest midterm too that we've ever had in this class. All right, moving on. So as you can see, I have 80% of my voice back. So thanks to all of you who showed up on Monday for our sort of awkward online QA. I'm excited to be back here in real life. So today we're going to talk about software engineering. And specifically, I want to give actually something you may not know is that back in the day, 61A, the class that you may or may not have taken, they had this property of the way lectures were structured, where Monday and Wednesday were the technical topics. And then Friday was like kind of a fun thing. So you get a guest speaker to come in and talk about privacy on the internet or to talk about some advanced topic in security or whatever. Yeah, that's just how it was. Now, over time, this is roughly the year 2000, 2001. I guess, sorry, still kind of noisy. I don't really mind. Over time, the classes grew, like 61A, like more and more material appeared. Similar thing kind of happened at 61B. So a couple of years ago, I tried to pare it back, especially now that we're getting towards the last third of the semester. We're all tired. We're all a little sleep deprived. So let's like ease up a little bit on the new hardcore technical topics and let's talk some philosophy, like kind of synthesize some more bigger lessons. So next 3 weeks, I'm going to do one lecture of the week just on this more broader topic so that we have a little bit of a breather. So the flavor here is going to be less technical, though today's is still fairly technical, but there's not like a thing that you need to know that would go on an exam, like a hash table or whatever. It's more something that I think will help you reflect on what we've done so far and it'll help you hopefully with project 2B and project 3, especially 3. Okay, so the motivation for the specific topic today is that in 61A and 61B, for the most part, we kind of misled you about what it means to program. So think about a 61A programming, right? You're given a program and the structure's already there and there's just a function. It's just like write the code that does this well-defined thing, that computes Fibonacci numbers or whatever it may be. 61B very similar. It's a little bit more abstract maybe where, okay, you're building a deck. And so the object has state and you need to be able to add last and add first. But again, like the things that you're supposed to do are very clear. N-gram map, time series, same thing. 2B is the first place where I think the programming is starting to resemble more like what you have in the real world, where you need to do something. Like I need hyponyms. Okay, hopefully you've gotten a chance to at least look at project 2B. And I need to generate these hyponyms and the data structures are up to me. I don't have some specific functions to write. That's part of what I decide. Okay. Now, the trouble with the way that we've done programming up to this point in your life is that always working at this small scale of there's a function and I just need to breathe life into it, it will cause you great pain later because you will not have the skills to go out there and identify the right abstractions and to pick the classes you want to create, to figure out what functions you need. And here and there, I've been like, write helper functions, all that. But the bigger question of system design is a very hard one. And I'd say that a lot of the upper divs, like for example, the operating systems upper div, yeah, it's about operating systems concepts, but it's also about just shoving you in the deep end and having you work with a group of people to figure out what the design ought to be. So in this lecture and in the next one in this series, I'm going to maybe give you a sense of how to deal with a large scale. Now, that's a hard thing to do in lecture because finding something big enough to be worth our time, but small enough to fit in lecture is pretty hard. So I'm going to tend to skew a little bit philosophical as opposed to concrete, but I think it'll work out well. Okay. Now, in the project 2B and in 3, you get a chance to actually experience this yourself, where for example, actually, I'll give the example a little bit. All right. And so I hope that what this will let you do is help you with project 3 and to reflect on what you've done in project 2B or give you tips as you're wrapping it up. Now, one thing I want to mention is that the structure of this lecture is heavily inspired by this book, which I have linked below if you want it. So if you want the longer story by the guy whose ideas I stole to give the structure to this lecture, John Osterhout's your guy. John actually, it's interesting, this book came to exist in part because his daughter, Kay, was a PhD student here, and she was a TA for me. And in spring 2017, our big kind of open-ended project was build a text editor, like a GUI text editor with word wrap and all that. And so it's a very hard thing to do in 61B. It's probably, I think, the hardest project 2 we ever had, like worse, I'd say, than the infamous Gitlet you might have heard of. And it didn't really have enough data structures content. Like, it was a cool project, but just wasn't data structures enough, so I abandoned it. But Kay told her dad, and then he used it as an assignment in his like upper division software engineering class at Stanford. And he found it really interesting seeing the mistakes or the good choices that his students made. And this book is in part reflections on that experiment. So it's like a full circle, 61B giveth, and then we take it back from John Osterhout. One fun thing, by the way, about teaching giant classes is that the GradeScope autograder, like, it didn't exist until I said, GradeScope, please build an autograder. And like, I worked with them and we like laid the groundwork. So often the things that just out there seem like they just exist. They're because there was some class with 1,000 people that had a need or an assignment, and then things happen. All right, anyway. Okay, so all of that preamble aside, let's talk about complexity. Okay. So I've said this before, but I think it's really worth repeating that I think one of the most unique things about the discipline that this class covers, that is building software and software engineering, is that it isn't really constrained by physics so much. Yeah, computers, they run at some certain speed and they have some amount of memory, but you just basically have to wait longer or not use as much data, but the program behaves like the program. And that's very different if we compare it to the challenges faced by people trying to do like, lab-grown meat. Like, lab-grown meat is not, it's heavily constrained by physics exercise. It's all about getting the temperature right and about like fluid flow and material science, or like fusion, right? Fusion power is the same deal, where people have been working on this for 70 years, like insane amounts of money have been poured into it, but it's an engineering challenge that's constrained by physics, and that's why it's hard. By contrast, what makes software hard is not anything about physics, but it's about our own brains. It's what we can fit in them. Programming is pure creativity. I don't have to worry about the temperature of my bioreactor. It's irrelevant. Doesn't really matter at all. Okay. And again, it's not 100% true, because again, we have some constraints. Like, I can't process, an exabyte of data in a minute, right? But the same principles you use to build the Ngram map work if your file is 100 megabytes or 100 terabytes. And so trying to build a system, like I want to build a better text editor than VS Code or IntelliJ, is only about being able to understand what you're building. It's, can you coordinate human effort to build the thing? You don't have to worry about physics. Or if you think about like Microsoft Windows or like the Apple iOS operating system, like they're just code. And they both started as like a line of code of someone writing like print, decades ago. But then they built on themselves over and over, and eventually there's thousands or tens or hundreds of thousands of people working on them. And but really, it is just their creativity, their ability to fit it in their brain that constrains it and make sure it works. Okay? So there's just some examples there that I already said. All right. So complexity. All right, we're gonna switch screen types. Sometimes my computer isn't happy. By the way, I recently used in office hours someone's new MacBook, and that 120 hertz screen was just so awesome. And I was like, I think I have to switch back now. Also, Windows. This laptop's kind of janky. I may switch back to Mac after a 6-year abandonment of Mac OS. Macs, they had this problem a few years ago where they switched to this like utterly terrible keyboard that felt like the travel distance was too tiny. Linux, myself and my office is Linux, and I actually kind of like having a different computer. Like every computer runs a different operating system. Then I can understand like setup issues for students, so, for reals. But like pure Linux is fine. It just could be a little fidgety. You know, I've been trying to use Linux as my primary operating system since the 90s, and there's always some stupid thing with like a sound card driver. So I just use the big operating systems because they have the vast amounts of money to be able to manage the complexity, right? Yeah, but I appreciate the Linux shout out for sure. All right, so anyway, so our limitation to making our Windows laptop properly connect to the screen is, well, in this case, it's both physics and software, but just having Windows work as a whole, that's a software thing. All right. Now here's the other thing. Programs generally start beautifully, but they eventually they acquire complexity. They gain more features. You add more tools to your Photoshop tool or whatever. And so that's where the problem comes in. Complexity creeps over time. And so over time, it becomes harder and harder for new programmers or even yourself to understand what the heck's going on. And if I want to modify my program, like if I were to go into IntelliJ today and say, I want to, I don't know, flip all the letters over for some reason, probably a lot harder to do that with the current code base than it would have been when it was new. And so there are tools to help us, like IntelliJ is a great tool for managing complexity because let's say I want to change a parameter from type int to type double. There's refactor functionality in the IDE that makes that possible. The IntelliJ debugger makes it really nice to be able to, if I make a change, I can figure out what I did wrong if it breaks. JUnit tests are really, really good because they let me make changes and then see if I broke my code. And of course, our visualizer, at least for small programs, they help us manage complexity. And really, that's why I introduced those tools in Project 1A, Project 1 and Project 2A and 2B. But the most important thing in terms of dealing with complexity is to avoid the problem in the first place, to keep our program simple. That's how you write good code. And if I look at your code today, versus if I were to wait 2 years and you come to my office hours and you decide to redo a project, maybe because you're a TA for me, and you redo, I don't know, array deck, what you'll find is that your code will just look simpler. And this is something you see in all kinds of different areas, right? Like if you watch somebody skiing who's really good at it, they make smaller body movements. They're not like curling or like snowboarding or whatever. You're not like moving your body so dramatically because you only need to move just a little bit. Or, if you're playing chess and you're a really good player, you're going to be able to identify like, okay, this is a position where I can find an easy move and I'm not going to spend a bunch of time on it. I know that this is not the time to expend my energy. I'm going to save it for later. Or, Dance Dance Revolution. If you play those dancing games, you watch people that are really good, like barely moving their legs, so like holding on to the bar, moving just like tiny steps because they've, again, optimized their process. So the same thing will be true for you. You'll recognize that you don't need to write 30 lines of code. Sometimes 2 lines of code is good enough. Think resize and array deck. Later, I'll come back to that. But that's an example where the way you write resize as a freshman or a sophomore or a newly entered junior transfer is dramatically different from somebody who's been programming in Java for a long time. Okay, so how do you manage complexity? Well, one is making your code simpler and more obvious. Okay, duh. And so what do I mean by that? I mean like the kind of thing like Sentinel nodes. So you might remember with a linked list deck, we had this property of the linked list deck that or actually it was an S list, where when we added to an initially empty S list, we would have a bug that would cause our add last to crash. And the way we fixed it at first was having a special case, but that's complicated. Turns out to actually be simpler to have a Sentinel node. And this idea of a Sentinel node, you'll see it in other domains where maybe you have a binary search tree where at the bottom of the tree, there's a Sentinel node that everything links to that's null. I've seen that occasionally. Or imagine having like an image program where you're like trying to do a flood fill, if you know what that is. Like I want to fill the image in with a color. maybe at the edge of the image, you have a dummy like pixel that, that's the end of the image, so that you never have a null around if you have a 2D array of like pixel objects or whatever. Sentinel nodes are very common. The other thing that you can do, and something that we've hinted at and hopefully you're getting a feeling for in 2B, is encapsulation into modules. So if you look at the spec in our project, I have this kind of weird warning out of nowhere about static variables in 2B, where I say, under no circumstances should you create a static n-gram map for this task. All right. The reason that I recommend this, and maybe you haven't gotten this far in the project, is that you really don't want to have what I think of as like a broad surface that anywhere in your program can like touch this thing. Like imagine if we had to communicate with each other and then there was like a glowing blue orb. Anytime you wanted to talk to each other, we have to touch the glowing blue orb. It's like, but then like maybe if someone touches the glowing blue orb with the wrong hand, it like, it starts leaking or something, right? Like then it's weird. Like you don't want to have a place that everybody's messing with something and it can cause changes that will mess with other processes that are accessing that same object. N-gram maps aren't so bad because they're immutable, they don't change. But when you have a mutable object that everybody can talk to, it's like, I mean, there have been serious problems in software development. One of the earliest cancer treatment machines had this issue where there was a global mutable state, and it was actually caused people to get killed by overdoses of radiation because people were trying to just hack together some software. And it was early days, people didn't know best practices. So the THERAC, if you're curious, the THERAC, pretty famous example of bad software engineering back in the day. So encapsulation into modules means you want your program to be built out of pieces that have very clear interfaces that don't allow you to have lots of crosstalk between a bunch of different parts of your code. And I know that's a very vague notion, but when it comes to, for example, project 2B, we gave this example of maybe you want a graph class, maybe you want a WordNet class, but you really don't want to be blurring the boundary and having, like one big class that does it all. You want to break things into pieces that are testable that you can understand. Okay. And so in a modular design, the idea is that it works just when it's only you working on something. It's still useful to be modular, but this is especially important in a team project, like say project 3, where you really want to have well-defined pieces that other people can use or yourself, and you don't have to know how they work. And I've said that a million times. I don't think I really need to repeat that. The idea is it's like, there is a thing and you know exactly how it works. That's a great tool for managing complexity. Okay? All right. So what is complexity? I guess I haven't defined it. So maybe now that I've been telling you how to avoid it, what is complexity? Well, I love Oosterhout's definition because it's human-centered. Complexity is anything related to the structure of a system, software system, that makes it hard to understand and modify the system. Okay. This is like a very nice thing. It's like, is it, it's not in units of complexities or whatever. It's just like, if you want to change it, how hard is it going to be for you to walk out? So I'll give you an example of a very complex piece of code. The Project 0 2048 code, I'd say, is quite complex. If you wanted to go in and change it so that in 2048, it's now a 5x5 grid, it would be quite difficult the way that the code is structured. It works for its purpose, but it is a little funky. And some code is just inherently complex, and I'll come back to that in a little bit, but it's a lot of work for you to even understand what's going on. And actually, one of my gripes about 2048 is you may remember this one really annoying thing about the API for that project, which is you can only call move on a tile once. And if you call it multiple times, you get this kind of like jumpy behavior in how it behaves. Just a complex thing. It's hard to understand how to build 2048, given what we give you in some ways. And if you wanted to actually change the system as it exists in some fundamental way, it'd be super hard. So it comes in a lot of ways. It comes in a lot of forms, complexity. One is, well, even trying to understand how the code works. Some code is inherently hard to understand. Like, for example, imagine trying to build a differential equation solver that runs a little simulation of maybe a system of differential equations. Such code is going to be basically inherently complicated because the math behind like Runge-Kutta solvers is complicated. But another one is complexity could just be the amount of time it takes to make small improvements. Maybe the code isn't so complicated from the perspective of reading it, but maybe it has a bunch of redundancy so that if you need to change something in one place, you need to change it in 8 other places to make sure that it actually, that the change actually makes any kind of impact. Computer, why are you being slow? Here we go. And then the other couple ones are finding what you need to modify in order to make the improvement, or it can be sometimes difficult to fix one bug without introducing another. So this might happen if you have, some of you might have array decks that were like that, where anybody here do the thing where you're like, the sum's not working, I'm going to add some +1s or -1s and see if that makes the autograder pass. Okay, so if you did that, then you're getting code that ends up being pretty brittle because you don't really have a full picture of what's going on. And so that kind of code could be really hard to fix without introducing other bugs. Okay. And so as John puts it, if a software system is hard to understand and modify, it's complicated. If it's easy to understand and modify, it's simple. Okay. Simple words, but I think wise ones. Right. And so we can think about complexity as something that costs us something. And basically in a complex system, it takes a lot of effort to make small improvements. And in a simple system, bigger improvements don't require as much effort. So let me give you an example. One sec. I'm going to send myself this file as an email. Let's see if I have it available. Why did I name it hi.java? Oop, okay, hold on. I have to open my email. So I have to, oh boy, I'm going to edit the video. Okay, well, I'm going to turn this off. I'm going to blink the screen real quick. I'm afraid of what emails might pop up that might be from students. Okay, oh, I'm still sharing my screen though for the online people. Ah, no. It is complex. Okay, you guys can look at the midterm 1 solutions while I fix this. Okay, cool. Please look at that document. Well, good. My email took over 30 seconds to load, so we were safe. Okay, here we go. Sorry, I was having such a good time in my advising session that I ended up getting here slightly late. Okay. I hope you're having fun. We're going to do some more interactive stuff because I know that even listening to me talk for this long, I think I'm pretty fun, but there's only so much we can take. Okay, here we go. All right. So here's a solution for 2048. I want to pick on it a little and get a sense of it works. I'll say it was kind of dark, but so it is. All right. Okay. All right. Dark mode is not a good mode for the screen. I didn't know that in the first 4 weeks, sorry. Okay, so this works, but it is really complicated to understand. It's like, this is the exhaustive cases. Thank you, student, for letting me, I forget who it was now, but someone gave me permission to show this last time. But they basically enumerated all of the cases. So it's like, if you're only caring about the top 2 rows, this is the top 2 rows, then you have the top 3 rows case, then you have the top 4 rows case. And so this code is 1, obviously extremely hard to understand. And 2, if you wanted to change anything, it would just be quite difficult. Yeah. Any observations about this code that you want to throw out there? Yeah. So many magic numbers. Yeah, exactly. Oh, it's just brutal. But there's still loops, which is interesting. Yeah. It's interesting to wonder what the solution is with no loops, just only if statements. Yeah. Any other observations about this? I will post this recording, so I guess future semesters can cheat by just typing it in. Yeah. Yeah, it repeats itself so much. And that's part of what makes it complicated. It's like there's like a lot of symmetry here that could be improved upon. Yeah. Right. And so this is the kind of thing that, like, when I see a novice programmer write code like this, it's fine. Like, I understand. This is a good example of, like, someone had an idea and they're really going to go for it, right? It's like a very funny novice programmer thing where you can get there, in the same sense that, like, imagine you're at the train station and you're like, okay, I'm going to get to my destination. And you're like, one way I could get there is I can climb onto the tracks and I can just, like, sort of scoot my way to the next station. You're 100% right. You will get there, but waiting for the train and getting on the train is a better solution. Okay. And so it's that kind of thing that's really important to recognize when you're trying to learn how to program. All right, back to our slides. Okay. Where did they go? We lost them. Oh, they're in this tab. Uh-oh, we're in trouble. Okay, I got a plan though. Okay, here we go. Okay, gosh, I really ought to just Is it gonna just open my email? Oh, that's fine. That's just me. Okay, it's all good. It's an email to myself. Okay. I value your privacy. Okay. All right. Okay. So basically, complexity comes, there's two main ways that it comes to be. One is dependencies, which is when you have a piece of code that you can't modify independently because it is deeply dependent on something else externally you can't see. So for a blank example, why is that not there? So for example, if you have a piece of code that relies on super obscure libraries or like the interaction of two super obscure libraries, then it can be tough. Oh, I remember this slide being broken last time. And then obscurity is another one. So it's when important information is not obvious. So for example, in the optional multidimensional trees lecture, I had two variables called good child and bad child. And for those of you who didn't watch that lecture, the idea is that you have a tree you want to explore, and there's a good side and a bad side, and you should look on the good side first and the bad side second, maybe. And so naming the variables good child and bad child makes the code more obvious. All right. So let's talk a little bit about ways that we can make our code more obvious and talk about decomposition, which really ultimately is one of the most important skills that I want you to pick up in this closing third and change of the course. Okay. So here's a decomposition exercise. You guys have done this already in Project Zero, but one of the most important ways to make code obvious is to decompose into parts. That can be as helper methods, it could be as helper classes, or it could just be as pieces of functions. Okay, so let's think about 2048. Here's a couple of different game states. And so let's talk about maybe a couple different ways to decompose the 2048 tilt operation. Like, what are some helper methods that you might have implemented? I'll just take some thoughts out loud. Because you can write it, the way we just saw, but what are some examples of helper methods you might have tried? Yeah. Tilt row or tilt column. So tilting one column is a clear one because you just got to call it 4 times. That sounds good. Okay. Within the tilt column process, what might you do? Anybody write any helper methods, or like even just conceptually think of it as stages of a process? Yeah. Combine. What does combine do? Combines them? Nope. You gotta be more specific. Combine sounds nice, but we don't know what it is. It's got to be well defined. Otherwise, it's not nicely encapsulated. Yeah. Find the first non-blank. Right. So a function that finds the first non-blank is a great one. Okay. I like that. Others? Yeah. Like get the second non-blank? Right. Right. Okay. So I can imagine trying to get like get the first one, get the second one, see if they're the same. It's an approach that could make sense. And when you only have 4 tiles, probably the number of statements not that high. Other helper methods people tried. Yeah. Right. Where will you go? Like destination or something, or like where I'll end up. So for example, if you call it on this tile, where's it going to end up? Top row. So that's a function that's well defined. You give it a tile, it tells you where you're going to go. 16, if you ask where is it going to go, it's not going anywhere. It's going to be itself. So what I would encourage you, as you're working on project 3 especially, maybe project 2B, it's having that as a first class exercise. And in project 3, you'll have the advantage of a partner where you can debate this. Project 3, by the way, you're going to generate randomly generated 2D worlds is the idea. And so you can say, okay, what kind of functions do we want? And we'll have an exercise at the very end of this lecture and in next week's lab that are along those lines. But this exercise in figuring out what your basic moves are, to use that idea from the live Q&A last time, is, I think, a very valuable thing. So let's talk about a little exercise in decomposition here. 1 sec. Okay. All right. Oh, I skipped the thing I was going to say earlier. All right. So let's talk about this little decomposition exercise. So this is inspired by the lab next week. Now, we're still debating whether or not you're going to do hexagons or pluses. But I want to work together a little bit to talk about this exercise. So this is, anybody here ever play Settlers of Catan, the game? Okay, so this is basically a Settlers of Catan board generator. That was the lab spring 21. We're still debating whether or not to shrink it a little. But I wanted to spend, some time talking about this and get a sense of, if we wanted to approach this problem, what are the useful abstractions? Okay, so why is there only, okay, here we go. I need to figure out how my slides are behaving a little funny. Okay, all right. Right, okay. So I'm gonna keep going and hopefully my laptop behaves itself. Here we go. All right, so suppose we're trying to actually do this. I want you to think a little bit about ways we could decompose this world generation process. And I want you to think about potentially useful helper methods or classes. And so what I'm gonna do, since I've been talking a long time about philosophy, I want you to just maybe spend a minute or two, actually 2 minutes, either thinking to yourself about how you'd approach this problem of generating these worlds. And yeah, if you want, you can also talk to a neighbor. So I'll give you guys 2 minutes to think about it, and then we'll just debrief a little bit and talk about different ways we might structure a solution to this problem. So I'll give you guys 2 minutes. Go for it. Yeah, maybe you need 3 minutes even, because you gotta figure out what the problem even is. I'll zoom in on this. Let's get better. And let's assume that you have an abstraction that allows you to, this is just printed text. That's what it is. Okay, good. Actually, you know what? I don't want to call it print statements. That's confusing. Imagine you have a function that given an X and a Y and a character, it puts it on the screen. Okay, so that's your basic abstraction. Like if you want to put a little green quote right there, you know how to do that. Okay, anyway, go. Okay, one more. Oh. Okay, 1 more minute. All right, let's talk it through. See what we come up with. Okay, you're gonna do this in lab too, by the way, but let's see where we get in lecture. So I'm not gonna write code, but I am gonna write notes. Not this code. Yeah, we're gonna start with this, and we're gonna turn it into world generator. All right, cool. Okay, so what do you guys think? What are some classes, methods? What came to mind? Yeah. A class that has a graph. That's interesting. Okay, so a class that contains a graph as an object, something like this. Right. And so what's this class called? Catan, right? Oh, yeah. Oh, yeah. World of hexagons, I'll call it. Okay, cool. So then you have an initialization. It's an interesting conception. Not what I would have thought, but I'm curious. Let's see where we go. Right. So what are the nodes? All right. Okay. So then the graph G, each node is a hexagon. Okay. What are the edges? All right. That's interesting. So where I run into fear here is that edges don't inherently carry some sense of like space to them. Because I feel like the graph, I mean, it's interesting to wonder, could you make a graph algorithm here that's very intuitive? Maybe. I mean, actually, I think you kind of could. You could make it a graph. But I think a graph, okay, I'm going to say that I think a graph could work, but I think a graph is too general a structure for what we're trying to do here, which is a very regular pattern. So for example, imagine you could frame like linked list deck as a graph, where the graph is just like trivially like, just a row of nodes. I think you basically run into the same problem here. That's a really interesting thought. The other thing is like the recursive data structure version, like given a node, you basically have 1, 2, 3, 4, 5, 6 neighbors, like your north, northeast, north, southeast, etc. neighbor. It's like a very regular structure. So I think a graph is too general. That's my sense. I don't think it'll help. Yeah. What's that? We could do like a hex tree of some kind. Ooh, that's really interesting. So you have a node and then it has a hex tree. But again, I feel like because the structure is always exactly the shape, I don't think it's the right data structure. Cool. All right. Yeah. Other thoughts? Yeah. Okay. I'm going to say graph is too general. I don't think it's going to it's like going to feel good until you start trying to actually like make something appear. And then you'll be like, what do we do now? You've like kind of pushed you've delayed decision making without actually getting much out of using a graph. Yeah. Cool. Go ahead. Sure. Oh, I see. Well, I think again, like trying to use a graph, I feel like having a graph is not necessarily useful. I think the idea you describe of like filling it in a clockwise direction that kind of spirals in, it's an interesting thought. I think it's probably more complicated than you would need, but it's just, yeah. Right. Oh, you absolutely could. Yeah. But I still kind of feel like it's a little too high level. You guys are going very top down on me. Let's go the other way. Like when I say top down, I mean, you're thinking about like the overall architecture. Like we're going to build a graph. We're going to have like a data structure of things. But let's maybe go bottom up first. Yeah. So maybe we can find a 2D array. A 2D array. You're still going high level on me. What's the 2D array of though? Uh-huh. No. Right. Okay. Okay. So give me a characterization of these nodes. Why is it a 2D array? Well, maybe not a 2D array, but like we would print it out as a 2D array. So we have like a helper class or helper that parse that hexagon Mm-hmm. Right. Oh, this is really good. Okay, so 2D array of nodes and node knows its position. Okay, this is a classic design problem. You'll also see this in 2B. Okay, so classic design decision that's hard. Right, that's true. Well, the point being basically like, imagine if you're trying to implement chess. So one way you could implement chess is you could have like piece da da da, and then maybe a piece has an X and a Y. Like you'll see this kind of design where it's a little funny, like where actually I'm gonna make this more Java-y so it makes sense. We have int X and Y. And we're going to call this class piece. So it's sort of funny because it's like, should a piece know its own position or should the board know the position of the piece? And there's no right answer. You'll see that in a couple of places. You'll see that in project 3. Like, should a thing know where it is or should some higher level thing decide where it is? Also in project 2B, I interrupted my own sentence. In project 2B, there's this question of, let's suppose you have a WordNet class that uses a graph. Which one needs to be aware of the idea of words? Like does WordNet know what dog is? Does the graph class itself know about words? It's this funny thing about like, should the higher level or the lower level keep track of kind of the base level details? Anyway, all right, I'm gonna totally pivot though. Just be aware that this is a classic design debate that you're gonna run into, that you encountered. It was like, we have a 2D array of nodes and each node knows its own position. So what's the point of having like a structure of nodes? Why not just have like all the nodes? Okay, someone else. Yeah. Right. Of XY pairs. Right, okay. Right. So what does this function do? I'll just write out the comment. Right. I think I missed one thing though. So this function, give me a name for this function. Oh, right. Okay. And so what would be an example of this positions? Like that's one hexagon. Does one, is this a hexagon? Yeah. So I guess my question here, let me interrupt real quick. So if we did draw array of X, Y's, and then I gave it a list containing, let's see. So it's a list of points. So I give it 0, 0, and 0, 1. Is that a valid input to your function? Yeah, 3 inputs. Okay, got it. Give me types. Double X, double Y. And then a list. Points. I see. And so is this like, this could be any arbitrary shape, like a triangle or a fish or what? Got it. I see. Okay. So draws a things to draw at X, Y. Fair. If we're only going to do hexagons, I'm going to simplify our function a little. And I'll just call it like draw hexagon. And then I don't need this. And I'll just say, draws a hexagon at X, Y. Okay. That seems fair. I think that's a great function. If you wanted to support different sizes, you can of course also throw in an int s. Okay, so I think that this right here is an immediately super useful abstraction. And I think the planning that we were doing earlier, which was like about graphs or about a directed graph, I actually think in this case, starting this kind of bottom-up style is more fruitful because you're going to be able to immediately build some confidence. You can write this function, look at it, see if you actually get something that appears on the screen. Yeah, I don't know if I exactly replicated what you're going for, but I basically tried to simplify yours a little. So let's suppose we had a draw hexagon primitive, right? What is the XY? Let's use this as a working example. If I give it an XY, is that like the center of the hexagon or what? What do you guys think? So you and your partner have decided, yeah, we're drawing hexagons. Now you got to decide what the XY means. Yeah. Well, I guess my question is like, when I say XY, what is XY? Like, is the XY the middle, or what do you think it should be? Well, so the function draws a hexagon. So go ahead.
Center would be a little tricky, I guess, if XY are double center.
Right.
But it'd be nicer.
Right.
Quote unquote top left. Kind of
Right. Yeah. So I think center is hard. I left off a detail that you don't know yet, which is this is a grid world where it is actually integer spaces. So that I think maybe makes let's see, what do we have here? I didn't actually pay attention to what type you picked. Doubles. Okay, we're gonna change it to ints. There you go. So I think if it's doubles, then yeah, it's the center. I've changed it to int because that matches what the lab will actually be. And so your suggestion was XY is the top left corner, right? Okay, I agree with that. So I think that's a very nice abstraction. And you'll notice it took us a while to get there, and that's pretty normal. I want one more useful function. Yeah, go ahead. Right. Oh, so you could write a function that generates where all the hexagons should go. Absolutely. So that's one approach. I hadn't thought about that. So we could do a function that returns. So you might say, I want to have like generate hexagon top lefts. And so what this is supposed to do is it doesn't take any arguments. It just returns all the XY pairs. Yeah, maybe it takes like a size of the whole board. Yeah, size of universe. We run into a bit of a problem though, is that like we want it to return a list of XYs or something. So we'd be able to call this. How do we fix this problem? So you can't really like return a list of two different things. Yeah. Yeah, right. Make a point class. And then hexagon, you could do a point here too. Okay, so point P, and we have a list of points. And so between these two functions, this would work. There are other approaches. I'll just throw one more out just to give you a different way of thinking. We could write a function that does something like public static point, bottom right point P. And this one is easier to write than generate hexagon top lefts. What this does is it returns the top, the top left of the hexagon to the bottom right of P. I don't know if that makes sense, but basically the idea, let me make this clear and then we'll call it a day. If you call out bottom right on this hexagon's top left, you would get this point. It basically like is a function that lets you jump to one of your neighbors. But your approach might just be cleaner, like a function that just does the math to figure out where all the corners should go. Okay, that's it for today. I hope you found that kind of interesting. And the point is design is really hard and you want to have really concrete abstractions when you start. See you, everybody.